Hi, in today's video we will see different methods of evaluating performance of a model of regression type and clustering type. Since regression is a part of supervised learning, the method for evaluating the performance of different model is used is R-squared error. And clustering belongs to unsupervised learning type of model. We will use two different performance measures to compare two different models are internal and external evaluation of a cluster. And at the end, we are going to see how to improve a performance of a model using two important techniques like bagging and boosting. Let us start with supervised learning, that is regression model. We try to fit a model correctly so that predicted value by a model comes closer to the actual value of a given sample. Now, group prediction is having the difference between actual and predicted value, which is very lowest. Now, let us consider this particular example where over x-axis we have an area of a particular house in a given square feet, which is our input variable, and over y-axis we have value of an apartment in some units like in lakhs or in thousands or dollars in rupees, whatever be the unit of that particular value. Now, this input area or input variable is also called as predictor variable, and output variable is also called as target variable. A model in a regression is nothing but giving an equation of a line or a curve which defines the relationship with the x and y values. So we represent here a regression model as a line which is given by an equation y is equal to a plus bx. Now over this line, if you look at these green crosses, these are the actual value of samples which are observed from given data set. For a given sample, if they are plotted or used on our regression model, what will be the value which will be given by a particular model? So these highlighted pink circles are nothing but predicted value of a particular house. So any difference between actual value and predicted value is an error in prediction. So as you can see here, actual value is greater than predicted value. So the error between actual and prediction will be positive. But in some cases, actual value is lesser than predicted value. So the difference or an error will be the negative one. The difference between actual value y and predicted value y dash, which is called as residual. Now this residual must be very less for a good regression model. So if we have multiple regression models and for a model which is having lesser residual value will be considered as the best regression model out of given models. Now we calculate one measure of goodness for regression is R-squared error or residual squared error. So overall prediction of a model is given by R-squared error, which is also known as coefficient of determination. And this value of R-squared error always ranges from 0 to 100% or from 0 to 1. The larger the value of R-squared error is, the better fit regression model is. Now R-square is given as sum of squared total minus sum of squared error divided by sum of squared total. Now what is this sum of squared total? Sum of squared total is nothing but difference between actual value of a sample to the mean of a sample. And we will take its difference square, we will add them, and that value is our sum of squared value total. Say for example, for some given data, there is an input variable x, there is variable y, and for some value of x we are having some value of y, and likewise we having different values, and here we will have different values of y. So first of all, to calculate y bar, I will add all y values and divide by n. So if there are total n samples, I will add all values of y and divide by n. Okay, so this will give me y bar. Now I will take difference from y to the y bar. So whatever value that I will get over here as of y bar, I will take difference from this value. Okay, and this values will be substituted over here, and later on I will calculate square of this term, that is y into y minus y bar whole square, and that value is nothing but square of a term. So these terms are squared and written over here. Their summation, the summation of this row is calculated or called as sum of squared total. Now how to calculate sum of squared error? Now sum of squared error is nothing but, here we will add one more column that is called as y dash. Say for example, this is my regression line, this is my actual value of y, say 0.2 is there, and according to this model, if I project this line, it is predicting a value of 0.1. So this y dash is 0.1 for y is equal to 0.2. So we will calculate difference between y and y dash, that is this value minus this value, likewise this value minus this value, this value minus this value. So we will have final calculation of y minus y dash. Later on we will square it. So sum of individual terms square will be taken on, and at the end we will perform their summation. So addition of all these squared terms is nothing but sum of squared error. Now let us see how to measure the performance of a clustering algorithm. If a clustering model is there, we are actually in a unsupervised learning. So in clustering, we actually form a natural grouping among a data set. Say for example, we are given one data set and we are need to identify such set of clusters. So system is identifying different clusters or nearest group of samples that are having same characteristics. Now in this clustering, there are two major challenges. First challenge is that initially before model starts building and data is given, we are unknown that how many clusters will be built from a given particular data set. And second, if even we take input parameter as how many number of clusters are needed to be formed, then we can form same number of clusters over the same data with the help of by grouping different instances which are closer to each other. So we can make same number of clusters using different group of instances. Now apart from this challenge of making a cluster, there is one more challenge, is that how do we evaluate this quality of cluster that is being made by a particular model. Now we do not have anything to compare with. Just like in regression we have actual value and predicted value, in classification we have actual class and predicted class. Likewise we do not have any something called as actual group and predicted group. So we do not have any prediction value to be compared with. That's why we will evaluate clustering with internal evaluation and external evaluation. Clustering is assessed by its underlying data is called as internal evaluation of cluster. We evaluate two things on internal evaluation, something called as homogeneity of a cluster, that is the number of measured over the data samples which belongs to same cluster, and we measure heterogeneity of a cluster, which is measured using data points which belongs to two different clusters. That is measured with something called as Shillot's coefficients. Now Shillot's coefficient uses something called as distance measure to measure the distance between two data elements based on their similarity measure, and this value of Shillot's always varies from -1 to 1. Now how to create or how to calculate Shillot's coefficient for any data set where there are k different clusters produced by a particular model. We calculate Shillot's with as b of I minus a of I divided by maximum of a of I comma b of I. Now what do we mean by a of I and b of I? A of I is an average distance between ith data instance and all other instances in a same cluster. Say for example, if I consider this star as my current instance, I will measure the distance between this particular star and all other samples. Now this distance is measured using distance measure, that can be Euclidean distance, Manhattan's distance or Minkowski distance. It depends which measure we use. So this distance is calculated and we will take an average of all these distance is called as A of I. Let us assume we are working in cluster 1. So number of elements in cluster 1 is N1. And we calculate A of I as A of I1, A of I2 up to A of IN1. So this is my ith element and other samples in the same class is A of I1. So this is my A of I1, this is my A of I2, this yellow distance, this is A of IN. Likewise, I have calculated distance and divide by number of samples is giving me cluster A of 1. Now, if I am considering this particular sample as my ith sample, how to calculate B of 1, 4? Now, B of 1, 4, since this samples belongs to one cluster, that's why B of 1 is written. And we are now considering another cluster as fourth cluster. That's why we are writing B of 1, 4. That means distance between this cluster sample and this cluster sample will be calculated. Now here we have to calculate distance from the star to all other points distance. So if there are N4 number of samples, we will calculate distance from this sample to all other N4 samples. And those distance will be written as B14 of 1, B14 of 2, B14 of 2 up to N4. Okay, now we have total number of samples in cluster 4 is N4. So in order to take an average, we will divide this sum by N4. So this is nothing but by B14. In order to calculate B12, we have to calculate this ith sample and we will find the distance B1 of 2, 1, B1 of 2, 2, B1 of 2, 3, B1, 2 of 4 and likewise a distance to all other samples. Now consider there are total N2 number of samples over here. So we will have B12 of 1, B12 of 2 up to likewise we have B12 of up to N2 number of samples, and there are N2 samples, that's why we will divide total number by sum by N2, and this will be giving me B12. Likewise from the same sample I will find the distance to all other distances. There are total N3 samples and I will calculate B1 of 3 is B13 of 1, B13 of 2 and likewise there are B13 of distance, total N3 samples. To take an average, I will divide this sum by N3. I will now have B14, B12 and B13. Okay, and now we will at the end substitute these values in Shillot's width. So for a given example, Shillot's width will be Bi minus Ba, B of I minus A of I divided by maximum of A of I comma B of I. So this Shillot's width will give us the internal evaluation of clustering. Now we will look into external evaluation of clustering, which is given by purity of a cluster. So cluster is also assessed on a measure of how close results are there in each class as compared to its class level. That is nothing but a purity. Purity is an extent to which cluster contains a single class. Say for example, there are n data instances and we know that there are C different classes labeled and our model generates K clusters. So purity is measured as 1 divided by n summation of K clusters, that is for each cluster we calculate whatever is greater, number of cluster intersection. In this example, let us consider purity. Here in total, there are 6 samples in cluster 1, 6 samples in cluster 2 and 5 samples in cluster 3. So, n will be 6 plus 6 plus 5, that is total number of samples are there is 70. There are, as you can see, three types of data. First data is of X type, second data is of O type, and third data is of diamond type. So these are called as known class label C. Since there are three different symbols, I will say number of class labels are also 3. And here you can see there are three different clusters that are formed, which is nothing but number of cluster K is equal to 3. Now we will find out purity. Purity is calculated as 1 by n, that is 70, into summation of majority of classes in each cluster. Now as you can see in this first cluster, majority of samples are of X type. In second cluster, majority of samples are of O type, and in third cluster, majority of samples are of diamond type. Now calculate how many X samples are there in first cluster, because cluster X label is X, so we will calculate majority of it. So there are only 5 samples in first cluster of type X. Now second cluster majority is O, so we will calculate how many samples of type O is there in second cluster. So in second cluster 1, 2, 3 and 4. 4 samples are of O type. In third cluster we will calculate majority of samples. So majority is diamond, so diamonds are 1, 2 and 3 only. So 3 clusters, 3 samples are there. So purity will be in this case 5 plus 4, 9 plus 3, 12 divided by 70, which is approximately equals to 0.71. 71% as purity. So this is an external evaluation of a cluster. For comparing any two different clustering algorithms, we would also come Shiller's measure and its purity both. So once model is selected, we need to improve its performance. We can improve the performance of a model in many ways: by giving a good training example, by tuning it, or by making ensembling. Now what is giving a good training data set? If quality of data set itself is not good, then obviously the performance of a model is not going to be good. So we are skipping that part. Apart from good training data set, what else can be done? We can tune the parameters of a model. Parameters of a model tuning process is nothing but adjusting the fitting options of a model. Say for example, when we are using k nearest neighborhood, we can choose different values of k as our parameter and see, observe the performance of a particular model. So that is called as, by changing some parameter, measuring the performance is called as tuning the parameter of model for a performance. So likewise in neural network, we can adjust the number of hidden layers and number of backpropagation to tune the particular model. Now apart from tuning a particular model, we can combine the strength of different models to make a particular model as a strong model. That is called as a process of ensemble. Now the process of ensemble, in the process of ensemble, we try to increase the performance of a particular model by taking an advantage of combining different models together. Now these combined models are actually complementing with each other. We learn one type of data in a set by one model. If we are struggling to learn another type of data in a given data set by same model, we can give this data set to another model to learn some different discoveries. So here in ensemble, we combine different models of a diverse trend, that is called as an ensemble. It helps in averaging the biasness. If one model is very biased, producing very biased results, then we can use ensemble of that model to reduce that bias and also to reduce a particular variance. It combines weak learner algorithms so that in combination they produces strong learners. Now look at the process of ensembling. Ensembling is a process where first step is to build number of models based on training data. For different diversified models that are generated, training data subset can be varied using its allocation function. Now it is up to allocation function whether it gives same training data set to different algorithms or different part of the training set data set is given to different algorithm. Then we use something called as bootstrapping to generate unique training data set. Now, if we are expecting each model to work on unique training data set, but we have only one training data set, then we can use bootstrapping at that stage. And another alternative is that same data set can be used for each model, but here condition is that models must be of varying characteristics. Say for example, we use SVM. SVM stands for Support Vector Machine, Neural Network, K-nearest neighborhood, decision trees, and naive Bayes. Now, what will happen at the output produced by each of these algorithms? So, output of each algorithm is considered as an hypothesis. So, output of first model is hypothesis 1. Second model's output is hypothesis 2. Likewise, if we are implementing n models, then we have n hypotheses. And we have something called as combiner function. Now it is up to combiner function how it interprets these hypotheses and produces final output. In regression model, these hypotheses are nothing but values as an output to each of the model. Now these values can be taken mean of, and when this combiner, these algorithms are of classification type and different algorithms are giving different class as an output, we can take a majority voting. That means out of 3 different classification models, 2 are saying that class A should be our target class and 1 class is saying B should be our target class. We will take an vote of maximum, that 2 classifier is saying that target class is A, then final target class is said as A. So combiner also varies from model to model. Whether we are building regression model, our combiner function will be different. For classification, likewise for clustering, and for association, it would be completely different. Now there are 2 popular ensemble models. First ensemble model is called as bagging. A bagging is also called as bootstrap aggregating approach. Now it is the most popular and the earliest method that came into an existence for an ensemble. The method it uses for dataset generation is bootstrap sampling. That is nothing but random selection with sampling with replacement. And using bootstrap sampling, we are generating diverse data set from a complete one training set, and this training set is used to train different models using same learning algorithm. And outcome from each of this algorithm model is later on combined either by voting or by taking an average. The method of ensembling, that is a bagging, is very simple, but yet it performs very good for unstable learners such as for decision trees, where changing a small criteria can also impact the outcome very significantly. As you can see in this particular diagram, we have only one original training data set, and using bootstrap sampling, we generate different data set of same size. Okay, remember that bootstrap sampling uses sampling with replacement. So data set can be generated and we have different classifier algorithms or different learners over here. So this is nothing but an example of classification. So this is classifier 1, classifier 2, likewise we have P classifiers. And we have something called as combined classifier, which can take decision based upon the hypothesis produced by each of classifier. Now let us understand another ensemble model that is called as boosting. So this is another technique for ensembling, and where we are training our weaker model on a resampled data. So data are always resampled, and please note that it is an iterative technique while bagging is parallel technique. Data sets are generated in different forms and they are given to different algorithms in bagging. But in boosting, we are resampling but in boosting, what will happen? Say we have data set and this data set is given to a particular model. Now this data set is again resampled and we are adjusting some weights of a model. So this model where our weights are adjusted, same resampled data is given and then its output is produced. Now using this output, we have resampled the data. This data is again resampled. This model's matter weights are again changed or adjusted, and this resampled data is again fed to the system and output is checked. So this is an iterative technique where we are changing the parameter of a particular model based on resampled data by adjusting the weight. So outcome if this combined weight voting approach is based on the performance different model. There is a special variant of boosting that is called as AdaBoot or adaptive boosting. Look at this particular example of boosting. Say for example, this is a classification example where we have some positive and negative examples. So system has classified our samples in this partition. So towards the left of partition all positive examples, towards the right of the partitions all negative examples. But the performance of a classifier is not very good, since in our negative classification part there are also positive samples which are 3, which is greater than the actual partition number of samples in that positive partition. So what we will do, we will resample by increasing the weight of these falsely partitioned, falsely classified samples. So these 3 positive samples are now given more weight. As you can see, the size of this plus is increased as compared to all other samples. And later on we apply or run classification algorithm. Now classification algorithm found out that this is our classification boundary. Toward the left there are all positive samples and toward the right there are all negative samples. Again, towards the positive class there are 3 negative examples, and in our negative class itself there are only 2 negative examples. So we need to increase the weight or the importance of these 3 negative examples. So it is better an idea to always give resample of data by giving them weights. So final data sets appears like that majority of positive and negative samples are in the middle. So classification should take place such that these majority of samples should be there in their respective class. Say for example, if I take partition or classification at this stage, so majority of positive examples are there in positive class and majority of negative examples are there in negative class. So performance of this model will be much better than the previous 2 models. So the process that we have followed is called as boosting on classification. There is one more method of ensembling that is called as random forest, which is applied on decision tree, where we are refining or ensembling decision tree in order to generate its forest. We will look into the detail of this model, of this approach in our later videos. Okay, so in today's video we have seen how to evaluate performance of a regression model and a clustering model, and we have seen 2 different approaches of improving a performance of a model, that is which uses ensembling, that is bagging and boosting. Thank you everyone for watching this video. This is Munira Topia signing out.